Welcome to this lecture where we're going to talk about the definition of big O in the context of algorithm analysis. So again, we'll talk about algorithm analysis and a detailed view of algorithm analysis, which is T of n. We'll define big O, and then we'll explore the implications and parts of the definition of big O in detail. So we'll do some work with the definition. Now remember, as we talked about before, T of n is the time required. T is a function required by an algorithm on an input size of n, where n is the number of inputs or the size of the input. Every algorithm that we wish to analyze has its own T of n, and we have to go from the algorithm or the code to get a T of n. And we haven't talked about how to do that, but we'll do that in a future lecture. Now, things to keep in mind are if you have a T of n should be detailed, and it should count almost everything the algorithm does, including all the things like initialization down to at the beginning all the way to shutting down. So initialization, reading input, doing the main computation, which is likely where most of the work happens, but not necessarily, writing the output and shutting down. And as we've talked about before, we think of T of n as providing an output of steps. The units of T of n are steps. This is like time, but these are fixed time operations. If it helps you, you can think of these in terms of seconds or milliseconds or hours or years or months or whatever, but really what they are fixed time operations or steps. Now, calculating T of n, as I mentioned, requires going from the algorithm to a functional definition of T of n, and it requires understanding everything that the algorithm is going to do, but it's actually too much. It's too specific for our needs, but it's a starting point. So T of n is too specific, meaning that it provides too much information, and so we need to distill that information into something simpler. What we're really interested in is how does T of n grow as n grows to be really large? And when we say really large, we mean as n goes towards infinity. Okay, does T of n, does it grow exponentially? Does it grow linearly? Does it grow sublinearly? Okay, we're going to seek to use the tools of analysis, which we'll talk about in just a second, to simplify T of n to find what we'll call an upper bound. And the upper bound is a hopefully simpler function that grows at least as quickly as T of n and represents an upper bound on its growth. So that's what we're going to look at next, the definition of what we call big O. And it's just that, it's just a definition. It's not magical, but it can be very useful. And the definition, what it does is it allows us to relate two functions and how quickly they grow relative to one another. In this case, T of n is one of those functions, and f of n, which we'll define soon, is another function. And what we're looking to do is to find, if you have T of n from your algorithm, which gives you the detailed number of steps that the algorithm takes, let's find an f of n that grows as quickly as that T of n, but is hopefully simpler and is an upper bound. So here is the definition. This is really important. You should pause the video, read this to yourself, write it down, make sure you memorize this definition, because this definition will be on your exam, not just any exam. It will be on your midterm and it will be on your final exam to know this definition inside and out in this form. So say it with me. T of n equals big O of f of n if there are positive constants c and n naught such that T of n is less than or equal to c times f of n for all n greater than or equal to n naught. And usually when I'm in person with people teaching this, I make them say this over and over and over again. I won't do that on this lecture, but you are charged with doing that for yourself. Say this definition again and again, but let's go through these parts. And again, remember, this is just a definition. There's nothing magical going on here. And what we're defining here is big O. Here, as we know, n is the size of the input. It's the number of elements in the input or the size of the input. And as we know, T of n is a detailed function for the runtime of the algorithm, the number of steps it takes. And what we're seeking to do is we're seeking to find an f of n that is growing at least as quickly. F of n is another function. It's the function that we think of as the upper bound here. and it's hopefully, usually, simpler than T of n, okay? So we have a complicated T of n. We're looking to find a simpler f of n that makes this definition true. Again, big O is the term that we're defining. It's just the notation that we use. There's nothing special about it. It just gives this relationship. It calls up this definition is what it does. Now, these two constants, c and n naught, let's talk about these. C, as you can observe right here, is used right here. C is a positive constant that scales f of n. So it allows f of n to be scaled up by as much as we like without including the c inside of f of n. In other words, if we wanted f of n to be 10 times n, we don't have to put the 10 in f of n because the 10 could be in c, okay? So f of n can be even simpler for that reason. So c allows us to scale up f of n so that we can make f of n arbitrarily multiply by an arbitrarily large number. And this other constant, n naught, tells us where we care about large n. In other words, it's the beginning portion of what we consider to be large. We said as n goes to infinity earlier. Well, this is the starting point of where we care about the large values of n, okay? So for small values of n, less than n naught, we don't really care. This definition doesn't apply. But the value of n naught tells us where we start to care about large n. Okay, so how do we use this definition? Remember, this is just a definition. If we're given some t of n, we're going to look for a simpler f of n that makes this true. And we prove that it's true by finding or choosing c and n naught. Okay, so let's take this simple example. Suppose t of n is this very complicated function 3n plus 4, and f of n is this much simpler function of n. Okay, we can prove, quote unquote, or apply the definition of t of n is equal to big O of f of n. In other words, this t of n is big O of this f of n. In other words, 3n plus 4 is equal to big O of n. That's what we're saying here. If we can provide positive constants c and n naught that make this true. Okay, now, is it true that 3n plus 4 is less than or equal to n? No, it's not. But is it true that this is less than or equal to 5n for n greater than or equal to 5? That's what this is saying. If we choose c of 5 and n naught of 5, so this c becomes this, and this n naught becomes this, well then, yes, that's true. We can see that 3n is growing not as quickly as 5n. And if we think about the value of n naught, what do we have here? We have 15 plus 4 is 19 versus 25, right? 25 is larger than 19. And as n grows beyond that, it will still be, 3n plus 4 will still be less than or equal to 5n for any larger values of n. Now, I just chose these values of c and n naught to illustrate this. If I had doubled these, if I had chosen c of 10 and n naught of 10, that also would have worked. I could have chosen c of 10 and n naught of 5. I could have chosen c of 5 and n naught of 10. Any values of c and n naught that make this inequality work for large values of n, that works to prove or to show that t of n is equal to big O of f of n. Okay, so that's just, those are just hand-selected values. Let's take a look at this these exact functions and some other examples, and let's look at them graphically. Again, we have the same function. T of n is 3n plus 4, f of n is the simpler value or simpler function of n. If we graph these, we can see that t of n is here in black, right? The black represents t of n, okay? The green represents f of n, which clearly is not an upper bound for t of n. However, if I multiply f of n times 5, this is 5 times f of n, the red line here. Clearly, it is an upper bound for t of n, and I'm making a graphical argument here, but you would agree with me that 5 times f of n is going to be larger than 3 times n. I'm sorry, 5 times n is going to be greater than 3 times n plus 4, as we argued on the last slide. And also, if I choose n naught of 5, then we can see that going forward in this blue region and going off into infinity, this function is always going to be greater than or equal to this function. And that's what allows us to say 3n plus 4 is equal to big O of n. Okay, because we can choose a C and an N naught that make this true. And I've tried to demonstrate for you graphically what the C and N naught are doing here. The N naught chooses a region that we care about, and the C scales the f of n up to a function that is growing as quickly as we need it to, but it only is a constant multiplier. We can't multiply it times n or something like that. Let's look at another slightly more complicated example, okay? Here we have t of n equals 3n squared plus 6n, and f of n is n squared, okay? Clearly, both of these are growing at a rate of n squared plus something. This is 3n squared plus 6n. This is n squared plus nothing. If we graph these out, again, here's t of n in black. Here's f of n in green. And f of n doesn't appear to be growing as quickly as t of n, but 4 times f of n, which is this red line, is growing more quickly than t of n. It's an upper bound if we choose n naught equals 7. So in other words, c here equals 4 that we got from here, and n naught is 7. And you can see that at this point, and from then on, the 4 times f of n is growing at least as quickly as t of n, which allows us to say t of n, this t of n is equal to big O of this f of n. Or, in other words, 3n squared plus 6n is equal to big O of n squared. Okay, now this next example is very similar but slightly different. Watch the exponent on f of n. We have the same t of n, 3n squared plus 6n. We have now not n squared, but n cubed. Can we still say that t of n is equal to big O of f of n? And yes, we can, because we can choose c and n naught that'll make this definition true. We can say 3n squared plus 6n is equal to big O of n cubed, okay? Because here we have f of n down here in green, which is n cubed. This black is t of n, and this red is 2 times f of n. Okay, 2 times, in other words, n cubed. And you can see that at this point, from this point onward, for n naught of 5, 2 times f of n is growing at least as quickly as t of n. And again, this is a visual argument. But the point I want to make on this slide is, even if you've seen big O before, you may have always associated t of n with the lowest valued or tightest function f of n that makes it true. But I want to show you here that we can use a faster growing function like n cubed, like 3n squared plus 6n is equal to big O of n cubed, but it's also equal to big O of n to the 4th for the same reasons, and n to the 5th, okay? You probably can't see those, I just realized. So t of n is probably equal to big O of n to the 4th and n to the 5th, and so on, okay? This n squared is the dominating term. This is certainly growing at least as fast as that, but so are these, okay? As long as we can come up with a c and an n naught that make this true, then we can say this is true. Okay, last example. Here we have a function that is an exponential plus a quadratic, 6 times a quadratic, versus an exponential, okay? Notice that these two terms are exactly the same. So it seems like t of n is growing faster than f of n, and it is, but we can multiply f of n with that constant c, and we'll get something that grows faster. So again, here's t of n, Here's f of n. And you can see that t of n is indeed growing faster than f of n because it has this additional 6n squared. But if we scale up f of n by a factor of c equals 4, then we get 4 times f of n, which is growing faster than t of n, as long as n naught is greater than or equal to 7. Okay? So all these examples show us a way of thinking about the relationship between this complicated t of n, and these have not been too complicated because I wanted to keep things simple for this lecture, and a simpler f of n. As long as we can choose a c and an n naught that make the definition true, t of n equals big O of f of n. Okay, so how to think about this in closing? Big O defines an upper bound on the growth rate of this function t of n, or any function that we're applying it to. And an upper bound, you can think of this as the worst case behavior of an algorithm. Sometimes algorithms operate quickly, sometimes they operate slowly. In the worst case, how slow is it? That's the idea. And what we're trying to do is we're trying to come up with a simple bound of the worst case behavior of the algorithm, which tells us essentially a simple time limit for any n. So we now have a simple way of expressing how much time it will take, or at least how the time will grow as the input grows. And that's exactly what this is saying. A simple understanding of how the time required increases with n. Okay. And you may be curious why we've been talking about large n performance. Why only when n is greater than or equal to n naught? Well, we care about large n behavior because when n is small, then quote unquote anything will work. In other words, if I only want to sort 3 to 5 elements of an array, I could use the slowest sorting algorithm in the world and it would still sort it pretty quickly. But when n is large, then those things that are really slow will get really slow, and we're going to be concerned about fast growing terms. In other words, the terms in our t of n that take a long time, and because those are going to dominate the runtime. So we care about large n behavior because when n is small, basically any approach will work, and when n is large, that's when things really slow down. So we're going to go ahead and continue talking about big O and related functions in the upcoming lectures and working with them in addition to trying to come up with how do we get t of n. So come back for that.